Okay, so good afternoon. This is the lesson for physics for the ATPL exams. We're really only going to, I think, probably only going to cover 4 broad topics on physics. There is a little more, but mostly it's straightforward and derived from this, and will come up easily in the course. But the course is easier if you know a certain small amount of physics in these 4 areas. So what I'm going to start with is something about units and dimensions. Now, this is a very generalized fundamental piece of physics, which helps you to remember formulas, to work out formulas or work out errors you've made in formulas if you have made an error, and it's particularly helpful, strange enough, in things like mass and balance, where it can actually tell you how to work out things like floor loading and running load just from knowing the units you want the answer in. So so we're going to start with units and dimensions. Then I'm going to look at Newton's laws, and so this, of course, is key to everything we do in principles of flight, really. So Newton's laws apply to all mechanics, all moving objects, or objects we're trying to move. And so understanding of those and realizing how fundamental it is, how you can't change the speed of something without going into Newton's laws, or how something that isn't changing its speed must be obeying Newton's first law, is really helpful in understanding what's going on in your principles of flight, particularly. Then we're going to look at pressure, and I'm going to look at dynamic pressure and static pressure here, and discuss them. So we're going to discuss total pressure and inch into Bernoulli's principle, but also relate it to energy to show how Bernoulli's principle relates to energy, and therefore the circumstances in which Bernoulli's principle isn't complied with. So that is helpful in principles of flight, but also particularly in engines, particularly in turbine engines, where in parts of the engines, you have to understand that Bernoulli's law is not going to be applicable, and it helps you with how the turbines work, particularly. And then finally, we're going to further develop pressure into the gas laws. We're going to look at the probably 5 gas laws, so sort of Boyle's law, Charles' law, Gay-Lussac law. Combine those 3 into the ideal gas law, and then we're going to look at Dalton's law. Okay, so so that's the 4 broad topics I'm going to cover. Probably take an hour or just over an hour to cover that little lot. Right, so let's get the blackboard up. And yeah, so I'm going to start out here with units and dimensions. Units and dimensions. Right. The relationship between the units and the dimension is the dimension is the type of number, and the units tells you how big the measures of that type are. So dimension might be, and we'll say unit. Okay. So, for example, the dimension might be telling you that we have mass, and the unit would be kilograms. Yeah. The dimension, now there are complications to this, in that some dimensions are not as straightforward, some properties are not a straightforward single dimension. For example, force is not itself a dimension. Force is measured in, let's think, kilogram, sorry, F equals ma, which would be kilogram meters per second. So that would be mass times length time divided by time would be the dimensions of force. So it's not as simple and straightforward as that. However, from our point of view, the difference doesn't really matter. We can fake it. This isn't real physics. This doesn't work properly. But force acts like a dimension. Yes, we just said force has the dimension of mass times distance divided by it's distance divided by time squared. Sorry, I got that wrong. So force, the dimensions are distance, time, sorry, let's get this right, mass times distance divided by time squared, because it's measured in kilograms meters per second squared, because F equals ma, which is mass times acceleration. Acceleration is distance divided by time squared. Okay, so that's what the dimensions of force really are, but we can fake it and just say force is its own dimension and it's in newtons. That does introduce the fact that there are some fundamental units, yeah, and there are others that can be made of a combination of other units. However, we're going to generally ignore that for the purpose of what we need. We're going to use the simplest units and the simplest dimensions, effectively, or the simplest units, and not going to combine units. Right. Okay, so that's the basics of what a dimension is and how it relates to a unit. Yeah, so actually, going back, I could also have mass in a unit of pounds. So this is another way dimensions and units are different, in that I can measure one thing. So something like length is another fundamental dimension, is another dimension. It is fundamental. I can measure that in millimeters, or I can measure it in feet, or I can measure it in nautical miles, yeah, or meters, which is the correct SI unit. I can measure it in furlongs. Yeah, as the joke unit for speed, furlongs per fortnight, tells you, okay, yeah, time is another one. Time is another dimension. I can measure time in seconds. I can measure it in days. I can measure it in hours, and I can measure it in fortnights, or months, or years. Yeah, so that's how units and dimensions relate. Okay, so the reason it's important, and that is all background. None of that you really need to know in any detail at all. If I have an equation and I have dimensions on one side, they must equal the dimensions on the other side of the equal sign. Yeah. Now, in fact, I just use that fact to tell me what dimensions force comes in. Yeah. Now, that's one we're going to ignore because we use force in newtons, and on the other side, we're using kilograms and meters per second squared. And you don't really need to know that the newtons and kilogram meters per second squared are technically the same thing. What's important to me is something like, if I have a formula, speed equals distance divided by time, and I'm measuring speed, let's say in knots, it's going to be the distance in nautical miles divided by the time in hours. Hi, Michelle. Yeah, so just to quickly go back, dimensions are physical properties which themselves have units. Technically, dimensions are fundamental, so sometimes we're going to get mismatches of units because some units are a combination of dimensions. But overall, the dimensions on one side must match the dimensions on the other side of an equation. And for most of the equations we're interested in, that will be a simple case of meaning that the units on one side of an equation match the units on the other. Yeah, so here we have speed in knots on the left-hand side, and we have distance in nautical miles divided by time in hours on the right-hand side. And so nautical miles per hour is equivalent to knots. Likewise, we could have our distance in meters. So if we had our distance in meters and our time in seconds, we would have to have our speed, or the equation is going to give us our speed in meters per second. Yeah. Now, this also tells us this. If you're happy with this, this tells us why the unit for acceleration. So we know acceleration. Well, let's consider what the unit might be. I'm not sure. Okay. Well, if I've got my speed, which we've just said, well, the SI unit of speed is meters per second. So we'll take the speed in meters per second. And of course, that means a speed change would also be measured in meters per second. So let's put that in, because an acceleration is a change of speed over a certain amount of time. So if I know I've changed my speed by a certain amount over a certain time, and I divide the speed change by the time, which would be in seconds, then that will tell me the acceleration. So let's say I increase my speed changes. I increase my speed by 20 meters per second in 2 seconds. Yeah, that would be an acceleration of 10 meters per second each second. Yeah. So that's how we're doing this. So speed change divided by time. So 20 divided by 2 gives me my 10 meters per second each second. So what is the unit going to be? Well, here I've got meters divided by seconds. So meters per second is meters divided by seconds. But then I've got the time on the bottom of the fraction anyway, and that's in seconds. So okay, whoever just joined, I don't know your name because you just got his iPhone, but no, that's fine. I was just saying, whoever's just joined, your name is given as iPhone. If you want to put a name on, put it up, but don't worry if you just want to stay anonymous. Okay, so we've got speed change in meters per second, but also on the bottom of the fraction, we've got another second. Yeah, so we've got seconds times seconds on the bottom, so our acceleration must be in meters per second squared. And that's how we get our acceleration, or rather our units of acceleration, as meters per second squared. It's meters per second, but those two per seconds can be combined, as in, so if I multiply 1 over seconds, that's per second, by 1 over seconds, which is also per second, that gives us 1 over second squared, of course. This also applies. Let's look at that. Let's look at it in terms of another one that's good for per second is the wavelength frequency formula for radio nav. Okay, so anyone who's done radio nav knows that the formula is C equals F times lambda. And let's find the unit of frequency, yeah, from this formula. So C is the speed of light, in case you haven't seen this. So C is the speed of light. So because it's a speed, and because it's science, we'll measure that in meters per second again. And lambda is the wavelength, which we will give in meters. So what I can say is that over on the left-hand side, I've got units of meters per second equals units of meters for lambda, and I've got to multiply that by 1/2 for in order to get meters per second on both sides. So the unit of frequency is 1/seconds. It's often written, by the way, you'll often see it written as seconds to the -1. Anything to the negative power is 1/, that thing. Okay, so you might see this, by the way, written as ms to the -2. I won't tend to do that. Any scientist or mathematician would tend to do this. I don't tend to for the exam because people find it easier to do the division format, but you might see ms to the -2 is the same as meters per second squared. That means meters per second squared. They mean the same thing. Okay, so you'll see them written like that, but I will always write them as the division. So the unit of frequency is 1/second, and in fact it used to be called cycles per second, and a cycle doesn't have any units, so that's a full 360. If you've seen the maths lesson this morning, you will remember talking about the sine curve. So that's a full 360-degree wave of a segment of a sine curve per second. That's one cycle, the number of those per second. We now call it hertz, but the units of hertz is per second. Yeah, so there you go. Now that's a dimensional analysis where we've proved that frequency must be, well, if this formula is correct, which it is, that the units of frequency must be per second. Even though we call it hertz, it's a unit of per second. Oh, here's an interesting one that actually vaguely comes up in the exam: the lift formula. So if you're not using Pad Pilot notes, the lift formula is lift equals CL half rho V squared S. Yeah. If you are using Pad Pilot, the CL goes at the end. So from the next stage, it's not going to make any difference. So lift is a force. Yeah. And so we might measure that in newtons. So what's the unit, though, of coefficient of lift? Now, if you know what coefficients are, you'd immediately tell me there are no units. It's dimensionless, because coefficients are dimensionless. Doesn't matter. Let's prove that. Okay. CL equals. So let's rearrange this formula. If you don't know how to rearrange it, watch the maths video. But we're going to get lift over half rho V squared S. Okay. And so what are the units? So lift is a force. So if we translate this into unit space, so we've got force, that would be in newtons. We've just mentioned, by the way, that newtons aren't a pure dimension, so we can break that down into other units. We won't have to in this case, but we'll be fine. So divide by, well, half doesn't have any units at all, does it? Yeah, half is just a number. That is what we call dimensionless. It's not a thing, it's just a number. So that's got no units at all. Rho. Now, rho is density. I am going to have to change that into force. Okay, so rho is density. It's kilograms per cubic meter. Yeah. And V is speed. Yeah, V is speed. So it's meters per second. So meters per second, but it's squared, so we've got meters squared per second squared. Yeah, and S is meters. Yeah, okay, so we've got this bunch of units, and most of them cancel out. Okay, because on the bottom here, I'm dividing by meters cubed, but I'm multiplying by meters squared, then I'm multiplying by meters. So the meters cubed disappears. Yeah. Kilograms per cubic meter. Yeah, that's right. So Okay, yeah. So we end up with newtons divided by kilograms. Wait a sec. Have I got something wrong here? Sorry, my apologies. That should be meters. I knew I had missing a meter. Sorry, this is area, isn't it? Which is in meters squared. My apologies. So I've got meters cubed on the bottom. I've got meters squared times meters squared. So I end up with kilograms, meters. We haven't cancelled the seconds per second squared. Here we've got newtons. Here we've got kilograms, meters per second squared. But we also know F equals ma. Now, I'm going to assume, we're going to talk about Newton's law next, and we'll discuss where F equals ma comes from. So force in newtons is mass, which is in kilograms, times meters per second squared. So newtons is equivalent to kilogram meters per second squared. So we end up with kilogram meters per second squared over kilogram meters per second squared. Now, there is a better way of doing this. I should have done this in a different way first. Let's slightly change the formula, and instead of half rho v squared there, I'm going to put Q. Now, we haven't talked about pressure yet, but Q is dynamic pressure. Is everyone happy? Does anyone not know that dynamic pressure is half rho v squared? No? We'll do, again, as I said, we will discuss that third thing today. We're going to talk about the pressures. So Q is dynamic pressure. So what we have here then is a bit of a different thing. Coefficient of lift is lift divided by QS. Yeah. Well, the unit of lift is newtons. Sorry. So the unit of lift is newtons. The unit of pressure is newtons per square meter. Yes. So Q is a pressure. The unit of pressure is newton per square meter, and S is in square meters. So the square meters cancel out, and then the newtons cancel out, and 0. We have no dimensions. Yeah, that's a better way of explaining it. I might trim out the other way. That's a better way of explaining it, is to keep half rho v squared as dynamic pressure. I should have done that from the start. Sorry if you got confused by the last one. It's a bit more complicated. But we've shown that coefficient of lift doesn't have any dimensions. And in fact, the other thing we show, by the way, we can rearrange this as equals lift over wing area divided by Q. Okay, but lift over area is pressure. If we divide the total force, so lift is the force on the wing, and if we divide that by the wing area, that's force per unit area. So this is the pressure difference across the wing, the average pressure difference between the lower and the upper surface of the wing, divided by dynamic pressure. And this is actually a fact you're supposed to know, although it's not usually taught, because I don't think they've asked it yet. I think it might come up soon in the exams, because they're filling in a lot of learning objectives at the moment that have never been asked before. And one of the learning objectives is you're supposed to know what coefficient of lift is. And it's the ratio of pressure difference produced on the wing to dynamic pressure. Effectively, it's how efficiently you convert dynamic pressure into pressure difference along the wing, which is why it's always, it's never much more than 1. I don't think I've ever seen coefficient of lift that's even as far as 2. You get high coefficients of lift, but even at low angles, at low speeds, high angles of attack, it's not that high. Yeah, so it's the pressure difference divided by the dynamic pressure. Okay, and all of this comes from this dimensional analysis, or all the way we can do this comes from dimensional analysis. Okay, now let's look at a more useful thing that I would say you probably should use in the exam to make your life easier. So in mass and balance, we have to find floor loading or floor load intensity. There's different words for it, but floor load intensity. And I'll call that, I'll call it FLI. That's easy, so we know what it is. And let's say, for example, if you look at CAP 696, the floor load intensity diagrams for the 737-400, the MRJT, are given in, so the MRJT, they're given in, they're given in kilograms per square foot unit. Yeah, crazy unit. Now, why is that unit important? That's one unit that they can be given in. You might be given it in pounds per square foot, which is a slightly more sensible one. The King Air freighter I used to fly had all the units in pounds per square feet. You might find it's in kilograms per square meter. They're probably the only ones you'll find, but in theory there could be the other. There could be others. In fact, sorry, Dan, on the helicopter side for the Super Puma, you find it in decanewtons per square meter. The reason they use decanewtons is because 1 kilo weighs about 10 newtons. So they've turned it into a force, because in theory, kilograms per square foot, even pounds per square foot, is complete nonsense. You can't do a floor load intensity in kilograms, because kilograms is mass and you really want force. So they've been pedantic and turned it into newtons. Yeah, but don't worry, that's equivalent to kilograms, because 1 kilogram is approximately 1 decanewton. I don't know if you noticed that in the book. So that's in CAP 758 for the helicopter guys. So what use is this? This unit tells you how to calculate it. So if I want to do the floor load intensity for a 737 for the MRJT, so then my floor load intensity equals the mass in kilograms divided by the area in square feet. Whereas if I had a more sensible one, and say the Super Puma, which is in reality it's in kilograms per square meter, the floor load intensity here, I would take the mass in kilograms and divide it by the area in square meters. And notice that's the unit. The unit is kilograms divided by square meters, so you just do kilograms divided by square meters. If I want it in pounds per square feet, the floor load intensity is the mass, sorry, pounds per square foot, mass in pounds divided by the area in square feet. Yeah, so the unit tells you how to work it out. But what if you want to work out the maximum mass, for example? So we want to actually work out the mass, and we know the maximum floor load intensity and we know the area. Well, we just then need to rearrange this equation. Watch the previous video for the maths video for rearranging equations, but we can do it with the triangle technique, which most of you have seen. So my floor load intensity equals mass in kilograms in this case. Crying out loud, sorry, my kilogram symbol didn't work out well. So mass in kilograms divided by area in square feet. So if I want to work out my maximum mass, I multiply my floor load intensity by my area in square feet. Yeah, and that gives me my mass in kilos. So again, the unit tells you the formula, and you can then rearrange that formula if you need to. Yeah, so the unit tells you that in order to work out floor load intensity, which is in kilograms per square foot, you need to divide the number of kilograms by the number of square feet. It works equally well with running loads, by the way. So if we take the example of the MRJT running load, let's do running load. The MRJT has it in kilograms per inch. Yeah, so running load is the mass in kilograms divided by the longest length, or the length that's along the aircraft, in inches. Yeah. And so you don't need to remember anything about the formula, about how to work out running load or floor load intensity, because the units will tell you the formula. You technically don't even need to sorry, someone's just heading off. You technically don't even need to remember things like how to work out speed, time, distance, because again, the units of speed tell you how to work that out, and it makes life so easy with your formula, with your formulas. If you're doing that, yeah, if you know that the units have to match either side of the formula, it makes it so much easier to remember things. You do have to be aware that some units can be combined into other units. So we go to our F equals MA formula, and we've got newtons on the left and kilograms and meters per second squared on the right. That doesn't look as if it balanced. In reality, because of the nature of force, this actually defines newtons isn't fundamental, whereas mass, length, and time are fundamental. We actually define force in terms of mass, length, and time. So actually 1 Newton equals 1 kilogram meters per second squared, and you can deal with that. However, the ones you need to use, so if you come across one that doesn't seem to work like that, then but the ones you need to use are like the ones we looked at for the mass and balance, are fundamental and easy enough to develop your formula or remind yourself of your formula by recognizing that the units are the same both sides. Okay, if you've got no more questions about units and dimensions, I don't want to spend too much time on it. It is kind of fundamental, so, and it does help, I think, a lot to the way to think about physics. So it's worth going over. But the next thing is Newton's laws. Okay, so Newton's laws of motion. And these are really important to principles of flight. And it's worth remembering at all times that they must be obeyed, because then you can consider whether the situation you've got is a Newton's first law situation or a Newton's second law situation. And you can also look at Newton's third law and say, obviously, things like how a jet engine works are related to Newton's third law. It's known as a reaction engine because of that. But Newton's first law is that a body will remain at rest or in constant motion. Now, that's one to be aware of, because it means not only constant speed but constant direction. So if you saw the math this morning, or go over the math this morning, we talked about vector quantities. So the vector doesn't change. If its direction changes or its speed changes, it's not in constant motion. Okay, it will remain at rest or in constant motion unless acted on by a net external force. So internal forces don't count, like the expression, you can't pull yourself up by your bootstraps. Yeah, so you try and pull yourself up by your boots, you're just pulling the top of you down, but you're not putting an external force on the boots. but also that it's a net external force. So if you have two equal and opposite forces, then you're still in Newton's first law case. Now that's really important in terms of understanding the principles of flight, because that's the straight and level flight, or a steady climb or a steady descent, where you're not accelerating. Yeah, constant motion. So you're in steady unaccelerated flight. So you've got no change of movement. So that means all your forces must be balanced out. So there's zero net external force. In straight and level flight, or in a climb, or in a descent under power, you have four forces on the aircraft. Or in a glide descent, you have three forces on the aircraft. But they must balance out. And that's actually the basis of how we work out all the forces, work with all the forces when you look at flight dynamics of straight and level flight, climb and descent. What you're trying to do is balance all the forces out because of Newton's first law. In a steady descent, a steady climb, or a steady straight and level unaccelerated flight, there is zero acceleration. So there must be zero net external force. So those four forces, three or four forces that are applied to the aircraft, must all be in balance. And that's what we rely on to calculate what's happening to the aircraft. Okay, so Newton's second law is that a body will accelerate proportional to net external force and inversely proportional to mass. To the mass. Now this is, you will often have seen this written as the formula I've given you already, F equals ma. If you rearrange that, A equals F over m. So it's proportional to force, inversely proportional to mass. So when we say inversely proportional, it means, so if A is inversely proportional to the mass, it means it's proportional to 1 over the mass. If I double the mass, then I'm going to halve the acceleration here, aren't I? If I double the bottom of a fraction, I halve the total value. So that's what we mean by inversely proportional. So A equals F over m, and that rearranges to F equals ma, which is our familiar form. So you might have seen it expressed that F equals ma is an expression of Newton's second law. Now, the main cases we're going to consider for Newton's second law would be turns. Okay, so that means in a turn, we're accelerating. Anytime you change velocity, you're accelerating, and velocity has direction as well as speed. So even if you don't speed up or slow down, you are accelerating. A turn is an acceleration at 90 degrees to the path towards the center of turn. Yeah. So we still need a force to produce that turn, and that's why we need to bank. So the lift produces that, what we call the centripetal force. So that's the most obvious way we use Newton's second law. However, if we look at something like Bernoulli's principle, that relies on Newton's second law as well. Now that's really interesting, because Bernoulli's principle states that that total pressure remains constant. So if we get an increase in dynamic pressure, yeah, so dynamic pressure is, we've already said, half rho v squared. So assuming density remains constant, if we get an increase in dynamic pressure, that's because the speed's increased. Yeah. So if the speed's increased, then we've accelerated, which means there must be a force on the air. Well, if there's a force on the air, there must be a pressure difference. And this is what I'm going to talk about a little more in the pressure side of things, is that in order to produce a change in speed, we must have a pressure difference. And that actually is effectively where Bernoulli's principle comes from. It's actually from Newton's second law. Okay, so let's do finally Newton's third law, which is every action is usually expressed as every action has an equal and opposite reaction. Has an equal and opposite reaction. Now, what this means is if we've got two things that are next to each other, we've got body A and body B. If body A puts a force on body B, then body B puts a force back on body A. And the classic would be is if, in fact, let's make these spheres. So if I put a billiard ball, a pool ball, something like that, okay, if, if A hits B, it puts, A puts a force on B, B puts a force back on A. And so if A hits B, B goes one way, but A stops or potentially even goes in a different direction. In fact, this is actually a really useful way of thinking if you're playing pool, because that means that the force on your, if you want to know where the cue ball, in fact, if you want to know where the target ball is going to go, it's going to go off in the direction at right angles to the surface where you hit it. But also the force on the cue ball is going to be at right angle to the surface where you hit it, if you want to work out where the cue ball is going to go off to. Yeah, the direction of the, that's the direction of the force. But anyway, so yeah, so you have the target, the cue ball puts a force on the target ball, but the target ball puts a force back on the cue ball, and that's why the cue ball is deflected. Yeah, in a game of pool or billiards or snooker or whatever. And that's the equal and opposite reaction. It's also how, you know, or at least in part, how a jet engine works. So we have we call it a reaction engine. So we're accelerating air in one direction. And so we must be accelerating or putting, so to do that, we put a force on the air. And in that case, the air must be putting a force on the engine to give us thrust. Likewise, we can see that a wing must push the air down. You must get downwash behind a wing or from a blade of a propeller or a main rotor. Yeah, so this is why we get induced flow through a main rotor down. It's equal and opposite reaction. So the air puts a force on the aerofoil, whether it's a rotor blade or a wing, and the aerofoil puts a force back on the air. So if the air puts a force up on a wing, the wing must be putting a force down on the air. So you always get downwash behind a wing, and you can't avoid that if you're producing any lift. The only time you don't get that is if you're at 0G. Yeah. By the way, it's also why, remember when I talked about the net, sorry, not the net, it's the external force. Remember I said pulling yourself up by your bootstraps. But it's also why an internal force can't move something. Yeah, because if I can't lift my boots up by putting a force on them, because I put a force on the boots, but the boots put a force then back on me. Yeah, it's also why you don't fall through your chair. So I presume you're all sitting on a chair. Well, there's a force on you of gravity, and you're transmitting that force onto your chair. So let's say I weigh about 80 kilos, so I'm putting about 800 newtons of force onto my chair. Now, the equal and opposite reaction from the chair is about 800 newtons upwards. So I'm now balanced. I've got a down force from the earth of 800 newtons and an up force from my chair of 800 newtons. And so I've got no net external force, all because of a reaction force. So it's actually much more vital. People neglect Newton's third law, but actually the way the world works, it's vital. Yeah. And those are Newton's laws of motion. And when I teach, I don't know if, I mean, I know some of you haven't seen any of my videos or haven't done any tuition with me, but when I teach principles of flight particularly, I like to mention Newton's first and second laws quite a lot, because I'll say, look, your steady straight and level flight, you're in Newton's first law case. So there's no net force. All the forces must balance. Or you're in a turn. That's a Newton's second law case. Therefore, you've got to have a net external force pulling you through that turn, accelerating you towards the center of turn. Accelerate, and it's got to be at 90 degrees to the path of the aircraft. And that's why you bank, to produce that force using lift. The other thing I'll say is, look, if you accelerate without changing your attitude, let's say you're steady, straight and level flight, and you accelerate without changing your attitude, then your coefficient of lift hasn't changed, and we've got lift equals CL half rho V squared S. And so what's going to change? Well, if you accelerate, the speed's going to change. Nothing else has changed, which means the lift must increase. What that does is then we're in a Newton's second law case, and we're going to accelerate upwards. Yeah. Now, once we've accelerated upwards, we start a climb, and if we don't change the attitude, that means that climb itself will reduce our angle of attack, so reduce our coefficient of lift. So we will rebalance ourselves. So once we've climbed, once we start a steep enough climb that our coefficient of lift has reduced, and now again the forces are all in balance, we will stop accelerating upwards. So it's not going to carry on accelerating upwards indefinitely, but you have to consider that. You have to consider the case that if you're in steady, straight and level flight, and let's say you pitch up, so you increase CL, then you're no longer in a Newton's first law case. You come into a Newton's second law case, and you're going to have an acceleration upwards. Yeah. Or if you reduce your speed, you're going to have an acceleration downwards unless you increase your angle of attack. So I will often mention those, and it's worth thinking about what's happening with, particularly with Newton's first and second laws, to say, well, actually, I'm steady, straight and level flight, so I'm in Newton's first law. Or I've got no net external force, so I must be in steady flight. I'm not accelerating or decelerating. Yeah. Or else I'm now in an unbalanced situation. I've got an unbalanced force that doesn't have any other force opposing it. Therefore, I must be accelerating in some way, because I must be into Newton's second law. I talk about it all the time, Newton's first law cases and Newton's second law cases. Am I in balance in unaccelerated flight, or am I out of balance in forces and I'm accelerating and changing my, either changing speed or changing direction? And that can be up and down speed as well as fore and aft speed. So if my lift changes, I change speed, but I change speed upwards, or yeah, upwards or downwards. That's speed as well. Yeah. Does that make sense of Newton's laws of motion? Does that, and why they're so important to particularly principles of flight? Yeah, but other things as well. Right. We have to do that before we can get on to pressure, static pressure and dynamic pressure. P, S, and Q. Now, useful to know the unit, newtons per square meter. That's it. That's the unit of pressure, and it's force per unit area. So if you have a certain pressure over a small area, you can have a high pressure, but if it's over a small area, you don't necessarily have that much force. This is how hydraulics works. So thinking of, I mean, you guys have never, I've never driven a car without servo-assisted brakes, but old-fashioned brakes on cars relied on this, where you would have a master cylinder under the brake pedal, which would have quite larger travel than modern servo-assisted brakes, and you'd move it a long way, but producing a large pressure over a small area. And then at the brake caliper, you'd have a large area, and the pressure would be the same. So it wouldn't move very far, but it would have a lot of force because of the large area. So you'd put a relatively small force, but over a small area gives the pressure. And then at the other end, with a larger area, you get a much larger force. Now, that is how an aircraft brakes work. Aircraft brakes work. So if you look at the Brahma press calculations, when you do hydraulics in AGK, in the system side, then it relies on that idea of pressure. In fact, before we even go into static pressure and dynamic pressure, let's just talk about the nature of static pressure. So all around you in the room you're in, there is static pressure, and that is putting the same force. So you're in a room, so if we've got a certain static pressure here, that's putting the same force on the same area all around you. Now, because of the weight of air, that's not quite true. There is a slightly higher force low down than there is high up. In A liquid, that's more the case because the liquid is heavier, much denser. Water is about 800 times-ish as dense as air. But in the air, to a rough approximation, the pressure all around you is constant. Now, if I have a fluid, when I say fluid, by the way, that's liquid or gas. Liquids and gases are fluids, and they transmit pressure. So if I now put in pressure using maybe a piston, and I force that onto the fluid, I'm going to put pressure evenly all around that. Okay, all around on all sides of a sealed container, and it will put even pressure in all directions. Yeah, and it's going to be equal, and that in fact is how for example, your body doesn't get crushed by the air pressure around you. Yeah, you've got pressure inside and it's pushing out again. But it's also how a balloon can be expanded, because it puts pressure all the way out. And the force per unit area is constant all around. Now, they're the very basic principles of pressure and how pressure works in a fluid. Now, what happens if I have done that and I then open that hole up again? What's going to happen is the pressure leaks out here. So if this pressure is higher than the external pressure, then the fluid is going to leak out there, and it's going to jet out there with some speed. Now, of course, in order to accelerate that in this direction, to put a force in that direction, to accelerate fluid in that direction, there must be, by Newton's third law, okay, so we put a force on the liquid the liquid or gas, the fluid, to force it in this direction. By Newton's third law, there is pressure, there is force on the container in the opposite direction. So the container is putting force on the fluid, and now the fluid must be putting force on the container. It's easier to think of gas on this one, and think of a balloon. When you release a balloon, it will blow away. Yeah, because you're expelling the gas, and that's putting a force on its container the other way. But also, you can also think of it as the other thing you can consider. That will do that. But the other thing you can consider is I could put that gas, as I release that pressure, I could put it over an impeller. So an impeller is a sort of gas-driven motor, or fluid-driven motor. Sorry, it can be liquid as well. So a fluid-driven motor. So that's an impeller. So a turbine is an example of an impeller. Yeah. It's an impeller, or a turbine is just an example of an impeller. And it will move it around, and that can do some work. What that means is this static pressure must be energy. Yeah. That static pressure must be energy, because we can do work with it. We can take that static pressure and blow a balloon across the scenery, or we can take that static pressure and take the gas out of a sealed container with high pressure in it over an impeller and spin the impeller. That does work. Okay. So that must mean, okay, so in fact, we need to define energy. Okay, energy is a capacity to do work. Now, I don't really like this definition, but so work, unfortunately, the definition of work is that it's a transfer of energy from one form to another, because energy never gets destroyed. Yeah, there is a law of conservation of energy, which, to be honest, I'm not covering, because I hope you know, but we may as well just say, energy cannot be created or destroyed, but just transferred from one form to another. Yeah, we're ignoring the matter-energy equivalent. We're not going to do nuclear reactions, so we ignore matter-energy equivalents. So energy cannot be created and it cannot be destroyed. It can only be changed from one form to another. And so what it is it's a capacity to change something. And energy can come in the form of kinetic energy, which is movement, thermal energy, which is actually just a special type of kinetic energy, a randomized type of kinetic energy, because molecules move very rapidly. It can be potential energy, and that has many forms. That has gravity. So if I lift something up, it has gravitational potential, because if I release it, it can then release the energy I've given it. Chemical potential energy. That's a classic. A battery has chemical potential energy. Jet A1 has chemical potential energy. That's what powers an aircraft. We've also got electrical energy. Yeah. So there's all these forms of energy. And so what we can do is we can turn this. I should have added static pressure here, because static pressure is a type of potential energy. So we've got this potential energy here of static pressure. Sorry, I'm going to add another one here, which is elastic. So a spring has elastic potential energy. So you can compress a spring and then it will do work. Yeah, it will move something. So in this case, we can use the potential energy of the static pressure here, which, by the way, it technically is a type of elastic potential energy. And we can use that to accelerate the air and blow it over an impeller and move the impeller. Yeah, and so that's doing work. That can do something useful. Right. So that's what energy is. And that all I'm proving here is that static pressure is energy. That's the important thing. Is a form of energy. Because then I'll look at Q. Q equals half rho V squared. So Q is dynamic pressure. This is dynamic pressure. Does anyone know the formula for kinetic energy? So this is movement energy of a block of something. Does anyone know the formula from school? Okay. Kinetic energy is half mv squared. Now, these are remarkably similar. This is half, well, rho is mass per area, per volume, mass divided by volume. Yeah, times v squared. So this is half mv squared divided by volume, which is energy density. So it's kinetic energy per cubic meter, for example, if you use SI units. Right. So we've just said static pressure is energy. But think about it. If you have a very small container and a very large container with the same pressure in them, the large container is going to contain a lot more energy, isn't it? So really, static pressure is potential energy. I'll just call it PE for potential energy per cubic meter. And dynamic pressure is kinetic energy per cubic meter. Now, the reason, this is going somewhere in terms of aviation. The reason I say this is Bernoulli's principle. Bernoulli's principle states that if we take total pressure as being static pressure plus dynamic pressure, then total pressure is constant in incompressible flow. Okay, right. So we'll ignore the incompressible because we only ever use it in incompressible flow, in a flow. Total energy, total pressure is constant. But this is energy per this is potential energy per cubic meter, and this is kinetic energy per cubic meter. And so all we're saying, so what this is total energy, or total pressure energy, but total, so we're not, sorry, I should say total pressure energy per cubic meter. Well, the law of conservation of energy, which I've just mentioned, where you can't create or destroy energy, must mean Bernoulli's principle is true. So Bernoulli's principle is really just a restatement of the law of conservation of energy. Again, I assure you this is going somewhere, because turbine engines don't obey Bernoulli's principle. And in fact, what we see on the compressor and the turbine of a turbine engine, the rotors don't obey Bernoulli's principle, but the stators do. Okay, so in a compressor, the rotors of a compressor, rotors add energy to the airflow. The stators, constant energy. We're not adding energy at all. So what you find now, if you haven't done AGK yet, maybe come back to this later, but it will hopefully make more sense of the AGK when you do come to it. If you're doing this at the moment, you probably notice this, that in an axial flow compressor, they show you that across the rotors, the static pressure and the dynamic pressure goes up. And so it doesn't obey Bernoulli's principle. But over the stators, the static pressure goes up and the dynamic pressure goes down. So the total pressure remains constant. And so they obey Bernoulli's principle. Over a turbine. Now, this is the one they ask a lot about in the exam. The rotors remove energy from the airflow. And the stators are again constant energy. So depending on whether you've got a reaction turbine or impulse turbine, and depending which diagram you look at as well, I'm not going to go into this complication at the moment, but if you look at any of the diagrams, you should find that either both the dynamic pressure and the static pressure remain constant, i.e. the speed of flow and the static pressure remain constant across the stators, or one goes up and one goes down. Yeah, but then across the rotors, the total pressure must go down. Yeah, now it's a bit more complicated than that, because in at least one case, one of the pressures goes up and one of them goes down. I think the static pressure goes down and the dynamic pressure goes up, but only slightly. So overall, the total pressure goes down over rotors. Okay, so on a rotor on a turbine, the total pressure goes down. On a rotor on a compressor, the total pressure goes up. Yeah, and that must be the case because of the energy considerations. Yeah, so a compressor is putting energy into the flow, or the rotors of a compressor are, and a turbine, the rotors are taking energy from the flow. Stators obey Bernoulli's principle because they're not spinning, they're not putting energy in and they're not taking energy out. Yeah. There is a mild complication of thermal energy, but we'll ignore that. That only applies to the the bootstrap air conditioning system, and we ignore it. It doesn't matter. You just need to know you only need to know vaguest bit about that. But I get a lot of confusion from students on compressors and turbines as to the fact that they're not obeying Bernoulli's principle. Okay, and they don't have to. Okay. Okay, so that's how pressure works, and that's how dynamic and static pressure work, and how they are energy density. So pressure is a measure of energy density. Static pressure is potential energy. Dynamic pressure is kinetic energy. That's why Bernoulli's principle works. It's because it's a restatement of the law of conservation of energy. We can't create or destroy energy. Okay, so that leads us on neatly to the gas laws. How have I put two S's in gas? Damn it. That's the problem with writing when you're talking. Gas laws. You need to know 4 gas laws, and I hate this fact. Sadly, you need to know which is which. And I must admit, I always have to look it up unless I've taught it in the last few days. I always have to look it up. Now, they are fairly rational, so this is why I'm adding them to discuss them. They come into several different exams. They come into, you need to know the principles of flight. A couple of them come into, I think MET they even come into, but human performance, you do learn them as well, and maybe even AGK, I can't remember. But anyway, you do definitely need to know 4 gas laws, one of which just combines the other 3, and then Dalton's law, which is the law of partial pressure. That is met. Okay, so the first one we'll talk about is Boyle's law. Boyle's law is that the volume of an amount of gas, this is on a constant amount of gas, is inversely proportional to the pressure. Yeah. So if I reduce the pressure on a gas, it will expand. Now, to me, that's fairly obvious, but all it's doing is I suppose it's not. I suppose it's not that obvious. But if you think about a balloon, the easiest way of thinking about it is to think about a balloon. Now, if a balloon rises in the air where the pressure reduces, we know the pressure reduces as you climb through the air, it will increase its volume. In fact, there was, some time ago, there was a balloon that went to the edge of space. I should have looked up this picture before before I did the lesson, but damn it. If you look at a high altitude balloon, then it looks quite small and deflated when it first takes off. And what it's designed to do, here's a good picture. If we go over to here. So this is a picture of a balloon that's designed to go to very high altitude. And this is already fully inflated. Because what happens is the pressure inside the balloon isn't going to change. But of course, the pressure outside the balloon is going to change. And so, all right, no, sorry, the pressure is going to change inside the balloon. The amount of air inside the balloon isn't going to change. But of course, the pressure on the balloon is going to change, and the gas inside it's not air. The gas inside the balloon is going to equalize that pressure. So when the pressure outside the balloon reduces, the gas inside the balloon is going to expand against it. Yeah. That's one way of looking at it. The other way of looking at it is in terms of what pressure means. Pressure is a force per unit area. Well, how is that pressure applied by a gas? If I have a surface here and then a gas putting pressure on it, what happens is molecules of the gas hit the edge of the container to produce the pressure on the edge of the container. Okay, and that impact produces the pressure. Now, let's see, in order to increase the pressure without increasing the speed of the molecules, the speed of the molecules is related to temperature, so we're not changing temperature. In order to increase the pressure, I have to have more molecules hitting the edge. Now, in order to get more molecules hitting the edge, I have to have more molecules in a certain space. So to get that increased pressure, the molecules must be closer together. I'm having more molecules at the same speed hitting the edge of the container, and therefore the volume must be smaller. So if I increase the pressure, volume must be smaller, and to reduce the pressure, the volume must be greater. Yeah, so that's Boyle's law. To be honest, one of the reasons it's most difficult to explain Boyle's law is that it's actually, I hope it's fairly obvious, but just remember it's Boyle's. I don't know how you remember it's Boyle's law. You are supposed to remember. Obviously, you can reverse this, by the way. Pressure is also inversely proportional to volume. So if I increase the volume of something without changing the temperature or the amount in it, then you'll reduce the pressure. Okay, so these are all reversible. These formulas, these laws, gas laws. The second gas law is Charles's law. And Charles's law states that volume is proportional to temperature. Now, I have to make an addition to here to say that this only works at constant temperature. If I change the temperature, Boyle's law isn't obeyed. Yeah. So at constant temperature, the volume is inversely proportional to the pressure. Now, at constant pressure, if I keep my pressure constant now, volume is proportional to temperature. Now, this is something, again, I hope you're aware of. If you warm something up, it expands. So by Charles's law, if I increase the temperature by 10%, that's going to increase the volume by 10%. However, temperature is a weird thing because we usually measure temperature in degrees, either degrees Celsius or, if you're an American, degrees Fahrenheit. But the reason we call it degrees is that the 0 is arbitrary. So doubling temperature doesn't mean anything in terms of degrees. Okay, so we need to have the temperature in Kelvin, which is temperature absolute. Now, temperature in Kelvin is absolute temperature, and the 0 of Kelvin is minus 273 degrees Celsius. Yeah, so 0 degrees Celsius is 273 Kelvin. Notice there's no degrees for Kelvin because Kelvin is an absolute. Now, so that means that minus 273 degrees Celsius equals 0 Kelvin. At 0 Kelvin, there is 0 thermal energy. Yeah. Yeah. So at 0 Kelvin, we have 0 energy. And so that's the point. That's why it's no longer an arbitrary point. 0 Kelvin is the point where if you have a gas and you take it to 0 Kelvin, effectively it has almost no volume. Of course, it has the volume of the molecules only, whereas almost all the volume around you, in the air around you, is space between the molecules. Yeah, the molecules are extremely tiny amount of the air around you. If you consider, for example, water as a gas, yeah, it has about, let's think for water, it's somewhere around it's less dense than air, so it's going to be higher volume, somewhere around 1,000 times the volume as water as a liquid. Yeah, and then at 0 Kelvin it would have even less volume still. So to a first approximation, just to get an idea of it, 999 out of 1,000, or so 99.9% of what's around you is empty space between molecules. Yeah. So if you took the gas to 0 Kelvin, you'd lose 99.9% of the volume. That's the point. Okay. That's why this works. Yeah. Because almost all the volume is the gaps, and the gaps between molecules are proportional to the temperature. Yeah. So if you increase the temperature in Kelvin, you're increasing the volume. Or this is technically Charles's law is only an approximation because it doesn't account for the size of the molecules, but it's an approximation of around 1 in 1,000 error. So that's very good, a very close approximation. In fact, that's how they calculated 273 Kelvin. They measured the volume of gas as they reduced the temperature, and then they extended the graph to show where it would reach 0 volume, and they worked out it would reach 0 volume at about minus 273 Celsius. And so that's how, I think Lord Kelvin himself, I presume, calculated the the absolute zero temperature originally. Yeah, so the volume of a gas is proportional to the temperature in Kelvin. So if I increase, so if I have a gas, let's say at 288 Kelvin, which is plus 15 degrees Celsius, and I increase the temperature to, let's say, 30 degrees Celsius, well, that's going to be 303 Kelvin, isn't it? Yeah. So the increase in volume is going to be, so what's 303 over 288? Is 1.052. So we've increased the temperature by 5%. Yeah. What I could have done actually, the other way I could do it is I would say that the change in temperature is 15 degrees Celsius. So 15 over 288, so 15 divided by 288 equals 0.052. So that's 5.2%. So we've increased the temperature by 5.2%. So what's going to happen is we're going to increase the volume by 5.2%. Yeah, that's what it means. Now, I can't see them making you do questions much like that, but what you might have is, you are supposed to know the law, but I think on that one, you're more likely to be just expected to repeat the law. Anyway, that's Charles's law. Gay-Lussac law doesn't mean Lussac was gay. It means these are two names. Gay-Lussac law is that pressure is proportional to temperature, again at a constant volume. Now at a constant volume. So notice we've done three laws. One we've kept temperature constant, one we've kept pressure constant, one we've kept volume constant. Yeah. So what this means is, again, temperature in Kelvin. So if I increase the temperature from 15 degrees to 30 degrees, now I've got a 5% increase in the pressure if I keep the volume constant. So that means that's warming up a vessel, a sealed vessel. The pressure increases with the temperature. Yeah. Any questions on that? Now, these can be combined. If you do want to use them, to be honest, I tend to use the universal gas law, which combines the three of these, it's sometimes known as the ideal gas law. An ideal gas is a certain type of gas that obeys all these exactly. We assume zero volume for all the molecules and a few other things. Don't worry about what an ideal gas is. We're going to assume all gases are ideal gases, although it's only approximation. The ideal gas law is P times V equal, I'll just do it. PV equals nRT. PV equals nRT. So that's pressure times volume equals N times R. You can really combine those into one constant if necessary. N and R are, N is the amount of gas you've got. It's in something called moles, but it doesn't really matter. R is the universal gas constant, which corrects all the units, basically. It compares the units of pressure, volume, and temperature and gets them all right. So R would be different in imperial units to SI units, for example. So if we combine N and R, that will be a constant for that amount of molecules. Yeah, so you can combine them. So PV, so you can kind of ignore what N and R are. So what that means is that P times V is proportional to T. Yeah, and that is actually a combination of all these gas laws. And because look what happens if I keep, I'm going to another layer. If I keep volume constant, I've got the fact that pressure is proportional to temperature. Pressure, well, that's Gay-Lussac law. Yeah. If, on the other hand, what the hell? Oh, something's happened to my pen. If I keep pressure constant, I'm saying volume is proportional to temperature. So that's Charles's law. If I, on the other hand, keep temperature constant and put a constant there instead of temperature, that means pressure times volume is a constant. That means pressure, if pressure increases, volume's got to go down equally. So pressure is inversely proportional to volume, or volume is inversely proportional to pressure. So in turn, that's an efficient way of remembering. As I say, because I remember it from school, I always remember the full PV equals nRT. But this is an efficient way of remembering a usable form of all the laws. It's just you don't know which is which. Okay. I don't like the fact that you need to know the names of all these laws, because that's probably the hardest thing here. Because I've explained how all the laws work, probably in terms that you understand that pressure is proportional to temperature, and volume is proportional to temperature, and volume is inversely proportional to pressure. But knowing it's Boyle's law or Charles' law or Gay-Lussac law is completely irrelevant to the physics of the world. You know, reality doesn't know that Robert Boyle ever existed, or Ray Charles. No, it wasn't Ray Charles who found Charles's law, but I don't know who Gay-Lussac was, or I don't know Charles's first name either. But reality doesn't know any of those people existed. Yet, obviously, reality follows these laws, and that's the important thing. And the ideal gas law encompasses all of the laws. For calculation purposes. However, sadly, has anyone come across or made up a mnemonic for remembering which of these laws is which? No, I haven't either. I can't, off the top of my head, I can't think of one.
I think there was one, but I did this last year sometime.
Right. Okay. So yeah. So it's clearly not as memorable as some mnemonics then. Because I bet you still remember some of the more obscene mnemonics in aviation. Okay. So anyway, I would say, to be honest, I tend to remember this for actually doing calculations. And when I had to remember which name was which, I remembered them separately and didn't use them for calculations really. Just okay. That's the gas laws then. Any questions on the gas laws? Okay, good. The final thing then is Dalton's law of partial pressure. I don't think you need to remember it's named after Dalton, but well, I don't think there's been any questions. I think technically it's in the syllabus. Dalton's law. This is sometimes known as the partial pressure law, and this states that the total pressure in a gas is proportional to the sum, so I should say total pressure of, let's put it in a gas, yeah, sum of the partial pressures of the component gases. Now, the only time we really talk about partial pressures is in MET, and this is when we might talk about partial pressure, particularly of water vapor. But what you'll find is, right, partial pressure comes not from a mass. From the mass, actually it does, it comes from the mass contribution. So let's say air is on average is about 78% nitrogen, 21% oxygen, and 1% water vapor. Yeah. And so let's say at 1,000 hectopascal, we can say that the nitrogen has approximately 780 hectopascal, The oxygen has about 210 hectopascal partial pressure, and water vapor has about 10 hectopascal. If we add all those up, we get 1,000 hectopascal. That's what they're saying. And really, the only important thing for that to you guys is to explain the meaning of partial pressure. If I took out, if I had a gas at a certain, and I kept the volume of the gas the same and the temperature of the gas the same, and I managed to take out all the nitrogen and all the oxygen, what would be left would be the water vapor, and it would have that. Then the pressure in the container would then be about 10 hectopascal. If on the other hand I took out all the nitrogen and the water, then what would be left would be oxygen, and it would have a pressure of about 210 hectopascal. If the total pressure originally had been 1,000 hectopascal with this combination. Yeah. By the way, the reason I'm ignoring everything else is because the next constituent is carbon dioxide, which is about 0.04%. It's a very tiny amount, so that would be 0.4 of a hectopascal. So that's an irrelevant contribution, really. Yeah, so if I took out all the oxygen and water, I would have only nitrogen left, and the total pressure and the residual pressure will be 780. But because we've got all of those and at that temperature, so to work out the pressure from PV equals nRT, our ideal gas law, we end up with the whole thing equaling 1,000 hectopascal. Yeah. In fact, this can be derived from the ideal gas law, by the way, because the NR, so yeah, so the N is the amount of it, and the N basically is proportional to these, or rather NR is proportional to these. We ignore the fact that the N and R are two different things. From our point of view, they're just one constant. But NR is proportional to each of these. So we go through our PV equals nRT. And so, oops, so pressure equals nRT over V. Well, T and V are a constant. NR, as I said, is proportional to the amount you've got. Oh, look, there you go. So the pressure produced by that bit we've got is proportional to how much of it we've got. But yeah, adding up all the contributions from Dalton's law, adding up all the contributions gets the total amount. Yeah, that's it. That's all there is to go. It has implications for things like if I increase the humidity of this. Yeah, so let's say I double the humidity. Well, that extra 10 hectopascals has got to come from somewhere. So, or rather, that extra 10 hectopascals would make 1,010. So if the pressure, if I've increased the humidity but not increased the pressure, what I've got to do is I've got to take 10 off the other two. So we end up with, instead of 780 and 210, I end up with 208 and 772, roughly. Yeah, and it still makes 1,000. Therefore, I can still make 1,000 hectopascal. What that's meaning is for every part of water I'm adding, I must be removing a bit of oxygen and nitrogen. Yeah, if my pressure hasn't increased. So at a given pressure, if I've got more humid air, it must have slightly less oxygen and slightly less nitrogen. The reason that's important is because it's slightly less dense. So you might have heard the expression hot, high, and humid for performance. So hot, high, and humid is restricted to performance. Now in Europe, you're never going to get enough humidity, but in hot, humid countries, you might get enough humidity to have a small effect on performance. Yeah, and this is why. It's because water is actually, weirdly enough, water is less dense than oxygen or nitrogen. Yeah. The molecular weight of water is, well, oxygen is 16, hydrogen is 1 each, so this is 18. Molecular mass of oxygen is, each is 16, so that's 32, and molecular mass of nitrogen is 28. So for every molecule of oxygen or nitrogen you displace with a molecule of water, the gas actually gets lighter. Yeah, so this is why there's one or two questions been asked in the past. I don't know, again, I don't know if it's still in there. where you're expected to know that high humidity slightly reduces the density of air, and this is why. Yeah. But it also connects to how you can measure the humidity of air. You can measure the humidity of air with the partial pressure of water. Yeah. And with Dalton's law, that is it. I think we've finished the physics really. I hadn't thought of any more physics you guys needed to know. If I do think of something, I will do another short lesson on it. But I will also, I'll distribute this freely anywhere you might have found this. So if you don't, if you can't find this video anywhere, contact me. However